The first thing we're asked to find in this problem is the magnitude of the EMF induced in this slide wire generator. That's a familiar result, and it equals the magnitude of the magnetic field times the length of the slide wire times the speed v that the wire is pulled. Let's take a look, though, at Faraday's law to see where this result comes from. The induced EMF is minus the time derivative of the magnetic flux through the generator. The magnetic flux is the integral of B dot dA. For calculating this dot product, I'll choose the direction of the area vector to be into the screen, parallel to the magnetic field. That makes the flux positive, and it also chooses the positive direction of the induced current. By the right-hand rule, with your right-hand thumb in the direction of the area vector, your right-hand fingers curl in the direction of positive induced current. So that's our positive direction for current. It's clockwise. If we call this dimension x, we can return and evaluate the magnetic flux as B times the enclosed area. That's L times x. So the induced EMF is minus the time derivative of BLx. Only x varies with time, so we find an induced EMF minus BL times dx dt, minus BLV. I'll come back to that minus sign in a minute, but for now, let's just calculate the magnitude of this EMF. When you substitute values and calculate, you find that it's 3 volts. Now if we come back to this minus sign, we can find the direction of the induced current by remembering the positive direction of current is in the clockwise direction given by the right-hand rule. This current will be opposite that because of the minus sign. So the induced current will be like this, which I'll draw in red. In accordance with Lenz's law, the induced magnetic field from this current will be coming toward us inside the loop and going away from us outside the loop. That opposes the change in the flux as the slide wire is pulled to the right. So the induced current is in the counterclockwise direction. Part C asks us to find the magnitude and direction of the force required to keep the slide moving at a constant speed. There are 2 forces to be considered here. The first one is an induced force, and it equals the induced current times L cross B. The L vector is in the direction of the current, so in the slide wire that's directed up, and the right-hand rule crossed into B gives us an induced force to the left. If the slide wire is to be pulled at a constant speed, there must be an opposing force in the opposite direction, to the right, with the same magnitude. L and B are perpendicular, so the magnitude here is ILB. If we use Ohm's law, E equals IR, to eliminate the current I, we get this expression, the EMF times LB divided by R. And when we substitute values and calculate, we find that the magnitude of this force is 0.8 newtons. And we know from above that its direction is to the right. It opposes the induced force. Lastly, Part D asks us to show that the rate at which energy is being put into the circuit equals the rate at which energy is being dissipated in the resistor. The rate that we're putting energy into the circuit is the mechanical force F dotted into V. That's the instantaneous power. Those 2 vectors are parallel. So when we calculate, we find it equals 6 joules. The rate energy is being dissipated by the circuit's resistor is the induced current I times the EMF. Again, using Ohm's law, we can express this as the EMF squared over the resistance. When we calculate, we find that it also equals 6 joules. Energy is being removed from the circuit in the resistor at the same rate that it's being deposited by the mechanical work of dragging the slide wire to the right.